This is Andy Schweitzer, and welcome to a series of videos in physics in the chapter of motion. Today we are going to look at kinematic equations. Kinetic just means movement. Kinetics means movement equations. And I have a few of them sitting here on the board. We have the distance is equal to velocity times time. Pretty simple. Change in distance divided by change in time is velocity as well. If we have a large amount of time, we might say it's average velocity, but change in acceleration is the change in velocity over the change in time. We did show some derivation of these other equations, as they're more common. Sometimes we want to be able to measure velocity final, and if we have an initial velocity and a constant acceleration, so that's important. We have a constant acceleration. In this case, there is no acceleration. So we have a constant velocity. Very often we like to know how far we went, and this is referred to as the distance formula, or sometimes referred to as the S formula, where S is sometimes referred to as spatial or distance. And I'm going to rewrite this here, but the distance S formula is equal to, sometimes referred to as x1, which is the initial placement of the individual on a graphical sense. If we're at 0, that's fine. Then just put 0, but if we're at 10, then we want to know how far we went from 10, plus the velocity initial times time. Of course, if you're at rest initially, well then your initial velocity could potentially be 0. Plus 1/2 the acceleration times time squared. So this is a situation where we can change the acceleration if we want to here. If we don't need acceleration, we're at constant speed, then we're back to this formula right here. Okay. So all I'm going to do here is pick out a few problems that we could work on. Some pretty common problems would be problems where, let's say, actually probably the most common one would be a free fall problem. And we'll turn to the next page and just try some. But a free fall is referring to free fall is a situation where you simply have something falling. And of course we're going to neglect wind resistance, but gravity pulling something down is, and since we're going down, it's negative 9.8 meters per second squared. A few things you might want to note is that this thing is an acceleration. It's got the meters per time squared. It indicates acceleration. So every second our velocity gains an additional 9.8 meters in the negative direction. Alright, so I might flip back and forth this page just to grab a particular equation. I'm going to grab a few of these here, just kind of walk through them. Alright, so let's go with a race car accelerates uniformly from 18.5 meters per second to 46 meters per second in 2.47 seconds. Determine the acceleration of the car and the distance traveled. Alright, so let's just kind of jot this down. We have car, and I'm just going to pull the words out as we go. Accelerates uniformly from 18.5 meters per second. So this is a velocity, and it's important to label all of your variables, to 46.1 meters per second. And this is also a velocity, and I'm going to say if this is the velocity final, then this would be a velocity initial. And it did this in 2.47 seconds. It wants to know, so this is obviously the time, it wants to know determine the acceleration and the distance traveled. So as I flip back and look at what I need here, I'm assuming you could say, okay, well, I want acceleration. Acceleration is change in velocity over change in time. That's VF minus VI divided by your change in time, which would be final minus initial. So let's use this equation right here to get our velocity, or sorry, acceleration. Alright, so this is going to be Vf minus Vi over change in t. And let's just start filling our variables in. Vf is going to be 46.1 minus 18.5, so I'm going to have a positive acceleration. And then my change in t is just 2.47 seconds. That's the start minus the end. Start generally is 0. Alright, and in this case, my math, this gives me 11.17 seconds. Alright, and my distance traveled, I need a distance formula, and we really only have one true distance formula, that all-encompassing. This is our S form. We refer to commonly as the S formula. Alright, and I will rewrite that one down here. I have the S, or distance, equals x1 plus vi times time plus 1/2 acceleration times time squared. Now, this is my initial position, which is not given, so it's 0. Just we'll assume it's starting at the starting point. Plus my initial velocity, which is going to be 18.5 times my time. Alright, and then of course my time is just going to be the 2.47 seconds. So this is the amount of time, amount of distance I would travel just based upon my initial velocity. And then I'll add on how much I would have traveled based on the acceleration, which is going to be 1/2 acceleration, which we calculated in the previous question, and I rewrote this incorrectly. It should have been, I do believe, meters per second squared. That's my acceleration, and this is going to go to 11.17, and then my time is going to be squared at 2.47, and if I did all my math correctly here, then my distance traveled is going to be 79.7 meters. Put that down into place. 79.7 meters. Alright, so that's a very typical problem using essentially two of our formulas. The distance formula, which is pretty standard, and of course we have our acceleration one. This is actually part of the velocity formula right here. So that one was used, and then this guy is just a derivation of actually this formula right here. But either way, we'll try one more free fall problem, and I will put that into the next video, an example of a free fall.